All right, we are going to do section 9.5, which is the difference of perfect squares. We talked about the difference of perfect squares a little bit in chapter 8 when we were foiling. We're going to go ahead and do the reverse, obviously, and factor it. This is what it looks like, or what our answers are going to look like in the end. But let's foil this and remember what happens. First of all, if you look at the equation that we're going to be foiling, you notice that the numbers are the same, n and 5, n and 5, but the signs are opposite. Same number, opposite signs are what we call the conjugates. And we talked about that back in chapter 8 too, but conjugates just means that the numbers are the same and the signs are different. So if we FOIL conjugates together, first here gives me n squared, outside gives me negative 5n, inside gives me a positive 5n, and last gives me a negative 25. When you go to combine your middle two terms, negative 5n plus 5n cancels, which just leaves us with n squared minus 25. Now this, as an answer, isn't bad. We can just FOIL out the conjugates. We see that the middle terms drop and we're just left with two terms. The problem comes when I give you the n squared minus 25 and you have to find the n plus 5n minus 5. The concept isn't difficult. It's recognizing the difference of perfect squares that's hard. If you noticed, the first term, n squared, is a perfect square because the square root is n. The second term, or the last term, is a perfect square because its square root is 5. The other important component is the fact that the sign in the middle has to be subtraction, because the only way that our middle terms would have dropped out is if we had one of each sign, one positive and one negative sign to begin with. The one of each sign always leaves our last term negative, just like in any other thing that we FOILed before. So the fact that there's a subtraction sign in the middle is really important. So that is why we call it the difference, because it has to be subtraction, of perfect squares, because perfect squares means you could take the square root of each of those numbers and get a whole number, or each variable. So difference of perfect squares is two perfect squares with a subtraction sign in the middle. This is something you really have to watch for because it's easy to get caught up in it. Also, the difference of perfect squares is always going to be two terms. So in the past when we've had two terms, we talked about maybe I can take out a common factor, which is still something you want to look for. But you also now have to look for the fact that they might both be perfect squares, such as x to the 6th minus 49. Okay? Any exponent to an even power, any variable to an even power, is considered a perfect square, because the square root of a power, you just have to divide it by 2. So any exponent that is divisible by 2 is considered a perfect square. Okay, so x to the 6th is a perfect square because 6 is even. It matters that the power is even. Whereas the number itself is a perfect square if you can take the square root and get a whole number. So x to the 6th is a perfect square because it's even. 49 is a perfect square because the square root of 49 is 7. And there's a subtraction sign in the middle. To factor this, once you've recognized that you have two perfect squares with a subtraction in the middle, you put two sets of parentheses, and you take the square root of each term. So the square root of x to the 6th, all you have to do is divide that power by 2, because that's what made it perfect square to begin with. It was divisible by 2. So 6 divided by 2 is 3. So you put x to the 3rd in the front, because remember your answers are going to have the exact same numbers in each set of parentheses. Because x to the 3rd times x to the 3rd is x to the 6th. You just split it up evenly. The number itself gets taken the square root, so the square root of 49 is 7. Once you have the numbers filled in, the signs are opposite, and it doesn't matter which one you put where because the numbers were the same to begin with. So same numbers, opposite signs. The numbers come simply from taking the square root of each term. So write your two parentheses, take the square root of the first term, that goes in the front of each set, take the square root of the second term, that goes in the back of each set, and when you're done, the signs have to be opposite, one of each sign. So here you have to recognize it. You see that there are two terms, There isn't anything you can take out of both x squared and 49, so there's no common factor that you need to worry about. But then you notice that x squared is a perfect square because 2 is even. 49 is a perfect square because it's square root of 7. And there's a subtraction sign in between. Don't forget to check for the subtraction sign. So to factor it, you put your two sets of parentheses. The square root of x squared is x, so the x's go in the front. The square root of 49 is 7. They go in the back, and the signs are opposite. Number 2, you see that 9y squared is a perfect square. 25 is a perfect square, and there's a subtraction sign in the middle. Also, you should have seen at the beginning that there wasn't anything you could take out of both terms, but it is the difference of perfect squares. So you put two sets of parentheses. The square root of 9 is 3. The square root of y squared is y, so that first term gets split into 3y. The square root of 25 is 5, so the last term gets split into 5 and 5, and your signs are opposite. And that's it. This third one, there's nothing you can take out of both 16 and 9, but 16x squared and 9y squared are both perfect squares, and there's that subtraction in the middle, making it the difference of perfect squares. So you put your two sets of parentheses. The square root of 16 is 4, the square root of x squared is x, so 4x goes in the front. The square root of 9y squared is just 3y. And your signs are different. Number 4, you see there's two terms, and you know there isn't anything you can take out of x squared and 81, so they have no common factors. X squared is a perfect square because that is even. 81 is a perfect square because it's divisible by, or it splits into 9. However, there is an addition sign in the middle. There are no two binomials that you can multiply together to give you x squared plus 81. This is the sum of perfect squares, and that isn't factorable, so we're going to write prime because there's an addition sign in the middle. If you come across one of those, simply highlight or circle the addition sign so I know that you understand that's why it's prime, and just write prime. You still have to be aware of factoring out a common factor before you do anything else. So let's look at these. This has 48a to the third minus 12a. There are only two terms. So whenever there are just two terms to start with, you automatically look for a common factor. 48 and 12 are both divisible by 12. So you know you can take something out. So you take out a 12. 48, this term has 3 a's, this one has 1, so you can take out 1. And then once you take out the 12a, you are left with 48 divided by 12, which is 4. You had 3 a's, you took 1 out, so you have a squared left, minus 12 divided by 12, which is 1. And you had an a, but you took it out. Now you have to be careful because this 4a squared minus 1 is the difference of perfect squares. You're not done. The 12a stays on the outside because there's nothing you can do to it. But 4a squared is a perfect square, 1 is a perfect square, and there's a subtraction in the middle, so that one has to be broken up into two sets of parentheses. The square root of 4a squared is 2a. The square root of 1 is 1, because 1 squared is 1. And your signs are opposite. Now we are finished, and this is your answer with all those factors. Let's look at these, 50 and 18. So only two terms, so you're looking for something that divides both 50 and 18. 50 and 18 are both divisible by 2. X squared, but this term doesn't have any x's, so you can't take out any variables. 50 divided by 2 is 25. You have an x squared. Minus 18 divided by 2, which is 9. Again, stop and check what's left inside the parentheses. 25x squared is a perfect square. 9 is a perfect square, and there's a subtraction in the middle. The 2 that we took out stays on the outside, but the difference of perfect squares gets split up. The square root of 25x squared is 5x, so that goes in the front. The square root of 9 is 3, so that goes in the back, and your signs are different or opposite. This whole chunk is your answer. The next one, 27 and 12, are both divisible by 3. This first term has 4 x's, the second term has 2, so you can take out 2. 27 divided by 3 is 9. I had 4 x's, I took 2 out, so there are 2 left. Minus 12 divided by 3, which is 4. I had 2 x's, but I took them both out. Again, stop and look at what's left inside. 9x squared is a perfect square. 4 is a perfect square, and there's a subtraction in the middle. The 3x squared we took out just stays on the outside, but the perfect square gets split up. The square root of 9x squared is 3x. The square root of 4 is 2. Your signs are opposite. Last one, 20 and 5, 2 terms, so look for a common factor. 20 and 5 are both divisible by 5. They do not share any variables, so that's all you can take out. 20 divided by 5 is 4. The x squared is still there. Minus 5 divided by 5 is 1. Again, 4x squared and 1 are perfect squares with a subtraction in between. 5 stays on the outside. Difference of perfect squares gets split up. 2x goes in the front. 1 goes in the back. Signs are different. This one is extra long, so we gotta get its own slide. 2 and 162 are both divisible by 2. They don't share any variables, so that just leaves me with x to the 4th minus 81 inside. Again, x to the 4th is a perfect square because it is even. 81 is a perfect square, and there's a subtraction in between. The 2 stays on the outside. The difference of perfect squares gets split up. The square root of x to the 4th is x squared because you divide your power by 2. The square root of 81 is 9, and your signs are different. You have to be careful with these because you still have x squareds inside, so it's still a possibility that you have the difference of perfect squares. 2 is fine. X squared plus 9 is not the difference of perfect squares because there's not a subtraction sign. But x squared minus 9 is. So the 2 things we couldn't change just stay the same. 2 and x squared plus 9 stay there. But this last difference of perfect squares gets split up yet again. The square root of x squared is x. The square root of 9 is 3. And your signs are different. This whole thing in blue is your answer. Lots of different factors there. Lastly, if there's an equal sign that still hasn't changed, you need to set it equal to 0. So we'll move the 25 over. Once you have it set equal to 0, you see that there are only 2 terms, 4y squared and 25. You can't take anything out of 4 and 25. But 4y squared and 25 are both perfect squares with a subtraction in the middle. So the square root of 4y squared is 2y. The square root of 25 is 5, and your signs are different. Once you have that down, you have to solve it. So set each parenthesis equal to 0 and solve. Subtract the 5, so 2y is negative 5. Divide by 2. It's not evenly divisible, so leave it as negative 5 halves. When you do this one, the numbers are the same, but the signs are different. So you add the 5, so 2y is a positive 5. Divide by 2, you get a positive 5 halves. Whenever you solve conjugates like that, you're going to end up with the same numbers with different signs, just like you have inside the parentheses. The lazy mathematicians would write y equals plus or minus 5 halves, meaning both positive 5 halves and negative 5 halves. You don't have to write it like that, but you can if you want. And that's it. Here's your assignment, page 505. You go ahead and start working.